both as a student and
Uh,
then professionally. I'm the founding hardware engineer at a startup called Laminar that's been around for about 6 years now. We are out of Greentown Labs in Somerville and build and sell a custom line of spectral sensors and AI platform to run them that helps major food and beverage companies run their production much more efficiently, save a ton of water, save a ton of time and money. I was Harvard Mechie, class of 21, and led their SEDS program and their CubeSat. And before that, I was heavily involved in a couple of hybrid rocketry programs, especially out at White Sands Missile Range, doing like 700-pound class rockets, aiming to hit the Kármán line. Also do a lot of non-engineering things sometimes, reading RPGs, a lot of hiking up in New Hampshire. And yeah, happy to chat anything electronics. What is a PCB, first of all? EE especially is, I would say, rife with acronyms. So if you don't see one, please ping in the chat and I will try and explain it. But PCB is printed circuit board. Currently, it is the most common form of interconnection for electronic components. It hasn't always been that. It probably won't be that forever. But basically nowadays, if it's some form of electronics, whether it's super cheap or cutting edge, it's got PCBs or it is mostly made up of them. Historically, things used to be done point to point, so they just wire directly between individual like transistors. And then you had wire wrap where you had these automated tools to do that and just embed the whole thing in epoxy. And then PCBs are just really a very efficient like evolution of that for making things work. You also can get them in both rigid and flexible. Rigid is by far the most common, what you're thinking of if you think like a circuit board. Flexible is that, but everything's mounted on a sheet of plastic. Really, really popular in small electronics nowadays. iPhones, flexible FFCs or flexible flat connectors are both cables and circuit boards kind of all rolled into one and let you package things really, really tightly. And then, yeah, what is Kicad or Kicad? People will disagree on the naming of this one, but it is Kicad, I think, officially. It's a French project, so that's what they called it. But it's by far the most popular open source electrical design software. Has a bunch of competitors, none of which are free for the most part, except for maybe like DipTrace or some of them nowadays. And it has really, really kind of cornered the market of everyone except for the most like higher end companies doing really complex things because it's free and it's really about 90% as good as the best of them and way, way less expensive. It's also been getting dramatically better year over year. I think they have by far the best update cadence of any of the CAD platforms, mechanical or electrical. So I think in a 2, 3 years, it might just straight up be the best one on the market, regardless of price. Has kind of hit that critical mass point for an open source project. So really great one to be learning. If you learn it and then you go intern or work at a job that uses any of these others, Altium probably being the most common, Cadence Allegro X and pads as well being pretty up there. It's cross trainable. It's like going from SolidWorks to Fusion or Inventor. You learn the general schema and then you just have to learn all the new shortcuts. But yeah, so to talk through the workflow of how does one make a PCB? First, concept and testing, figure out what you want to make. Breadboards are still fairly useful nowadays, though with components getting smaller and smaller, they're harder to use. So figuring out how you can string together things on a breadboard, if it's discrete logic, like individual transistors and MOSFETs, or using dev boards. So Arduinos, open source boards, stuff from the manufacturer directly, but kind of like stitching everything together as best you can before ordering a circuit board is really helpful just because it allows you to get your general like logic worked out in a bit less permanent way. From there, you take it into building a schematic. This traditionally was drawn out by hand. Nowadays, you draw it in one of these tools. And you're basically taking your effectively like a whiteboard sketch and turning it into a like detailed engineering drawing of this. So you're trying to account for what every single pin of every single component, what is it connected to, and what is the intention behind all of those connections ideally. And doing this in a like neat enough and organized enough way that you can understand it and that other engineers looking at this design can understand it. There's lots and lots of best practices around this. Generally, I'll say the number one things to keep in mind is having some sort of like flow across your drawing. So like all your inputs come in on the left and then they flow to your like logic section and they flow to the outputs is really helpful. You can use hierarchical sheets where you have like sub-assemblies and then assemblies if you're familiar with like mechanical CAD terminology. Using nets, using clean labels, sticking with like consistent capitalization and spacing on labels really helps as well. And just generally like trying to not cram everything in as tight as possible. You're probably not printing it out anymore. It doesn't all have to fit on one A4 sheet of paper. Just make the schematic bigger and get it spread out neatly. Yeah, parts assignment. Kicad has a somewhat unique approach to parts mapping. Most CAD platform or most ECAD platforms are use what are called atomic parts. So like the specific resistor you put on the schematic is a specific resistor. So it is intrinsically has a footprint, has a value, and everything assigned to it. KiCad doesn't do that way. You add components first in their most generic form. So you just add resistor R9 and then you go in and you set the characteristics of that resistor. This is somewhat different than, yeah, like Eagle especially, or Eagle or Altium, if you're familiar with those. You can import atomic libraries for KiCad. If you don't, just know that this will be the main difference from learning a different one. I actually have grown to prefer KiCad, but I do build atomic libraries from work, just because sometimes you want to know exactly which resistors you have in stock, and then preferentially use that specific one you have in stock rather than going and selecting a new one. But this is the point where you go through your schematic and you find a real part to correspond to everything on it that was generic. So generally, if you're building a schematic, you'll have your like specific parts of like this specific op amp I want to use, this specific voltage regulator I want to use. But then their data sheets will say things like just, oh, put a 1 microfarad capacitor on the VN pin to ground. And this is where you go through and you go to DigiKey or you go to Mauser and you say, okay, I want a 1 microfarad capacitor. It needs to be rated for 5 volts. I maybe expect this to be a high temp board or something. So you narrow your list down and you choose a part and figure out what size it comes in, choose the appropriate size, select it, put it into your bill of materials, and move on from there. From there, we'll go through PCB routing, which is basically take all of these parts and move them from this just like conceptual drawing into the PCB editor and start actually like figuring out how do they all fit together. We'll come back to this a little bit as we get into the routing stage, but generally you want to kind of start routing thinking about what are the core parts of this board that can't change. So form factor, if you're saying I want it to be a Pi hat, like it needs to fit on top of a Raspberry Pi. Well, there's connectors and there's mounting holes and there's a general shape that you need to follow. So you start with those. And then you work through putting your major things on it. So your microcontrollers, your critical sensors, anything with lots of pins and lots of critical functionality. And then kind of work down the priority list of what needs to go first, second, and what can kind of just be crammed in around the edges as needed. Finally, do things like cleanup. Silkscreen is all of the like text and markings. You can do cool art with this. You can also just make sure everything's labeled so you actually know what's on the board. Check assembly process. It's really helpful to, at this point, once you have your board like done, take a look at it and say, okay, if I have a pair of tweezers and I'm trying to put this together, like what's my sequence of doing so? Could I actually do so? Are you going to assemble it? Are you going to send it out to a shop to be assembled? If you are going to be assembling it, you should probably buy stencils. You need to make sure you have all the parts, solder. And then I always like to do a final check on mounting holes and alignment features because those are really hard to go back and fix later. Yeah, I'll come back to ordering a PCB and other resources. But I want to pull up KiCad and we can kind of take a look through it. I have version 9 set up on this machine, which is the most recent stable, or close to most recent stable. When you open a project, this is the default window you get. So KiCad breaks files down into schematics and PCB files. If you're using an older version, this might be called Eskima and PCB new, which are useful to know in case you look at any like older tutorials. I would say KiCad V7 and newer is all very similar. 5 and 6 are relatively the same, and 4 and older are quite different. So I would not look at tutorials older than maybe 6. But like a 7 or 8 will be quite comparable in terms of like where all the buttons are. Yeah, schematic editor, edit your project schematic. Symbol editor, these are your symbol libraries. Kicad comes with a lot of libraries, like part definitions already built in. For this, I'm going to only use things out of that. But many manufacturers publish libraries of all of their parts, which can easily be forked in. Basically any part that's on DigiKey or Mouser is going to have a KiCad available file ready to be pulled in. If it doesn't, you can go in and make your own. I'll leave that for a future tutorial. It's not terribly hard. PCB editor, this is where you edit the like graphical file that actually represents the PCB and how it will be physically constructed. And footprint editor, this is how you edit the graphical file that represents each individual part on it and how they will be assembled. And then it gives you a set of useful tools down here. Gerber viewer, we'll come to that at the end, but this is lets you look at your like final production output files and just verify things. Image converter, you can either use it to like map things in directly to schematic symbols for old parts. You can also do it for some helping with some of the like fun silkscreen art. Calculator, this is just kind of a general set of EE calculators. So for things like how big does this trace need to be? How hot will this get, depending on how many watts I put through it? Is my RF trace balanced to 50 ohms or not? Useful stuff. Honestly, useful if you're taking a like intro EE course as well. Has some of the formulas kind of already plugged in. Drawing sheet editor, we're going to ignore that for this, and plug in a content manager similarly. So yeah, open up the schematic and kind of talk through a really basic design here. Go through, put it on a PCB, lay it out, and then open it up for questions. All right, I was playing around in this to test. So what we're going to do for an example here is lay out an Arduino shield. So pull in basically the format of an Arduino, and then we're going to implement a sensor on top of it. And I chose a sensor for this that I like using. It works quite well, but it's really, really small. So it's very hard to do on a breadboard or any sort of like hand assembly. For adding things, you can go over here. Everything in KiCad has keyboard shortcuts, which can all be customized, but the default layout is pretty good. Place symbols or A brings up basically just the giant set of library of what's already built in here and what you've added so that you can go through and put it on a board. Recently used, if we just search Arduino, they've loaded in a few of the basic ones here. So we're going to pull in an Uno R3, about the most basic you can get. And then we're going to pull in, and you can see it keeps the tool up, so you can just click again and it'll execute the same command. Going to pull in an SHT4X. This is a very popular, very high performance, tiny little temperature and relative humidity sensor that operates over a protocol known as I2C. And you can see I still have the tool pulled up here. So now what we're going to do is I'll pull over the sensor data sheet onto the shared screen here. And we can look at what's actually required to implement something like this. So very basic little sensor. He basically has a little membrane, can measure how much humidity is building up on there, and then a really good temperature sensor and reports out over a digital process. For this purpose of this, I'm going to kind of skip through most of this data sheet and just take a look at our typical application circuit. So this is just what one actually needs to do to wire this up. So we need to connect SVA to SVA, SCL to SCL as per standard I2C. We need pull-up resistors between each of our I2C lines pulled up to our supply voltage, VDD, or our digital supply voltage. And then it needs a decoupling capacitor of approximately 100 nanofarads between digital supply and ground. This sensor only has 4 pins, which makes this fairly straightforward. So how do we do that? First things first, take a look at our Arduino footprint. So this guy just basically has defined all of the pins that are on an Arduino. And so if you've worked with an Arduino, you know that it has onboard power regulators. So you connect it over USB and it produces 5 volts from that, or passes through 5 volts from that and produces 3.3 volts from that. For this guy, he needs to run on 3.3. I'm going to presume for the purposes of this guide that it's 5-volt compatible, which I think it probably actually isn't, but just for this one. So how do we do that? We could just go and directly wire between. That would work, and that would define a connection that we could then implement on the circuit board. But we're going to make it with a net just to make things a little bit neater. So we'll hit P, or place power symbols. What that does is it gives us these kind of generic power symbols that you'll be familiar with if you've looked at any other like schematics before. And what these let you do is really clean up your circuit board, your schematic here. So I'm just going to copy paste one over for both, and then we connect these. Now anything that's connected to one of these ground symbols is going to be connected together. And so now we've defined like our ground connection for this full schematic. We're going to do the same thing for power. So we'll connect a 3v3 here for anything we want to connect to that power rail. And the same thing for 5. Awesome. And now what we remember from the data sheet, we need 2 resistors and a capacitor as well to finish this out. So for just a generic capacitor, we just type in C, and we get unpolarized capacitor of the most basic sort here. And this guy needs to go on this board between VDD. So you can see we can just run a trace, click it in. Same thing to ground. And if we double click on it, it pulls up its specifics. So for this capacitor, what we know is we need it to be 100 nanofarads, 0.1 microfarads. And we'll get to footprint in just a minute. Updates here shows you what we've specified that capacitor as. And now we'll do the same thing with the 2 resistors. So these are just under R. There's other different drawings and like ways to depict them if you like the squiggly resistors, if you like smaller ones and you're trying to fit more things onto your board or onto your schematic. But for this, we'll just go with a standard resistor. We'll turn that into a 10K resistor. And then we will copy paste it. And now we have 2 of them. For this, copy pasting on it is super helpful because you're just going to have tons and tons of things that are all the same. And once you set one resistor, it's really nice to just be able to make a bunch of duplicates of it. But we want to connect SDA to SDA, SCL to SCL. Of course, they overlap like this. Why would they not? And then each of them needs a resistor. And then pulled up to the appropriate voltage. So that is, in a nutshell, the very most basic set of schematic here. The final thing you have to do on the schematic tab, and then I'll run through and we can talk, or like take questions on this stage of the process, is assign footprints. So this button here or the bomb thing next to it. What this basically says is, hi, you've got all of these schematic symbols, but we don't actually know what they look like, and so we don't know how you'd put them on a board. For some things, like an Arduino, it has a very specific shape. There's only one Arduino, and so it is preset in there. And this SHT4X, same thing. That's a specific branded sensor, so it has a shape already loaded. But there's a million manufacturers of capacitors, so we have to tell it what size of capacitor do we want, how do we want to put it on here. For these, it helps if we go to SMD capacitors, surface mount devices, and THT is through hole. So through hole are the ones with little wires sticking out that go into a hole on each side of it. SMD are ones that you solder flat onto the board. I usually work with SMD stuff from doing small electronics. Through hole is way, way easier if you're building the board yourself. We'll do one of each for the purposes of this. So we filter to just that set of footprints. And then we have about a million different sizes of them, right? 103 different sizes of them. All of these CP Elect ones, those are some brands' custom sizes, or actually, no, those are just bigger ones. The custom ones down here where you can see a brand attached to it. All of these that are, say, like 0x, 0y, or bigger, these are a standard set of sizes that you'll see across resistors, capacitors, diodes, anything fairly basic. And they are just like the measurement in each side, each direction. You'll see it'll say like 04, 02, and then 1005 metric. So 04, 02 in inches, and then 1005 in millimeters. Most people use the inch sizes on these just because. If you're building the board yourself and you're not trying to fit everything in really, really tiny, I would not go smaller than 0603s. 0603s, 0805s gives you a lot of options and good performance in those and good pricing without getting way too small. If you're building this commercially, 402s are typically the sweet spot of machines can place them very easily. Humans can still work with them, though it's starting to get harder, and they're small enough to get you most of the size savings. And if you're building iPhones, you're going to be using 0201s really heavily. Anything where you're trying to fit everything in with the minimum sizes, 0201s, and then there actually are smaller sizes than that. But for this, an 0603, if you're building it yourself, these hand solder pads are quite helpful. They just makes the pad a little bit bigger so you have more room for a soldering iron. So we'll assign that. And then for these resistors, we want to go down. We'll grab the resistor sizes. And for these, we'll do through hole ones. They've got all sorts of different variations of these. Basically just defining like length and then the diameter of the resistor and whether you're expecting to stick it vertically on the board or whether it'll lay horizontally. So let's select just two of these horizontal ones that look about standard. Great. And now we have a footprint assigned for everything. Hit OK, and then we'll save and close this. And this gets you to pretty much like the minimum viable schematic for building an Arduino shield. Does anyone have any questions off of that? Nope. Alrighty. Now we'll launch into the PCB editor side of things. So this is the sister tool in Kicad. Right now, I have nothing on it, but what we want to do is hit our Update PCB from Schematic, or F8 button, and what that will do is pull in our most recent schematic and put all of those parts on this board for us. Alrighty, you can see I've got the outline of an Arduino, 2 resistor footprints, a capacitor footprint, and 1 tiny little sensor. Before we start putting anything on here, just a general lay of the land. On our left has all of your like settings tools for just how does the board look. Do you want to see copper? Do you want to see the inverse of it? Do you want it to show you these like little blue lines indicating what is supposed to be connected to what? Or do you want to hide those? what size units do you want to be in? Do you want to have a grid? Do you want things to snap to the grid? Honestly, the default set here is pretty useful. Middle right, we have our set of tools. So this is place footprints. If you wanted to put something that's not on your schematic, you can place it here and then backport it to the schematic if you wish. Route a single track. Tune length match, which we won't talk through for the purpose of this. Add a via, which is a hole to connect layers, which we'll talk about in just a minute. Filled zones, shapes, text, and then measuring tools at the bottom. PCBs are fabricated as a set of layers. So you can effectively think of them as basically if you were just drawing all of the features on a sheet of paper and then stacking those sheets of paper on top of each other and stapling them together to connect between layers. So things that are on your front layer are not touching electrically your back layer at all, unless you put what's called a via and connect them intentionally at that point. To make this make a little bit more sense, we're going to first start by going into board setup at the top left here. And we'll talk through a little bit about like what is a PCB. So first thing you should do if you are starting with one of these is take a look at your physical stack up. These are the layers that actually make up the PCB. So on top we have silkscreen, which is just our like printing, literally silk screening like printing a shirt, but it's just to add text or labels or anything on top. Paste, which is the solder that connects everything together. I think I'm getting chats, but it was being covered up there. Yes, I can address these questions real quick and then we'll get back to it. Difference between VIN and the 5.5 or 5v5 there. On the Arduino, I actually think they are connected. VIN is literally like whatever is coming in over the USB on the Arduino. You can power most Arduinos and most clones with something that is not exactly 5 volts. So my guess is the 5-volt label is coming after any protection circuitry that they have there. In terms of development of your own boards, that is a huge question that will get you lots and lots of Reddit threads, lots of Stack Overflow, etc. Generally, if you're doing something basic, Arduino is outdated, but extremely well documented. The main microcontrollers in use in it are old. All of the app megas are old. They even internally have started switching to using much more modern things from Renesas, SAMD 21s as well. Much more modern. ESP32s are very popular. They are way, way, way more powerful than Arduinos. They have a lot of quirks. They ESP32s are from just like a fairly small Chinese board like chip design house that basically set out to build the cheapest possible Wi-Fi attached microcontroller so that you can do things like smart home. If you want to make your light bulb connect to the network, the microcontroller in use cannot cost very much if you want to do that and still sell the bulb for $5. They did really well at that. The documentation is very bad. Most of the documentation you'll find in English is community supported, and they've gotten a lot better on their more recent ones. I use them for a lot of projects. Not where I would recommend for starting unless you are certain that it needs to connect to the internet. If you don't need network connectivity, I would steer clear of them. Generally, if you're looking for somewhere actually to get started, I would say RP2040s, which is the Raspberry Pi one. They're about $1 each. The full board is about $5-6. Very well supported, very performant, and quite well documented. But generally, if it's your very first one, I would still stick with an Arduino. I think the documentation is the very best, and they have the least expectations that you know how to code to get things working. Both the others require a little bit more. ESP32s and RP2040s and STM32s and all that can be pulled into Arduino as well. But million different options. Every engineer is going to tell you something different. I use a lot of STM32s for work. I use RP20s for work. I use a wide variety of weird ones for personal projects because I just want to try different things. So all over the place. But yeah, back to layers of a board. So you have your solder paste. This is the like little metal and paste mixture that is put on top of the board to actually solder things together. So this gets added only right when you're about to assemble. Solder mask, that's what makes a PCB green or purple or black. It's the color that's printed on top. And that's added because that ink that they print that with repels solder. So it makes it so that your solder stays only where you want it to be, and it kind of just like hydrophobically squishes away from the colored sections of the board. Your copper layers, which is what's making all of these electrical connections dielectric. This is FR4. It's basically just fiberglass. It's what gives the board the physical structure. FR4 is literally fiber resistant for fiberglass, fire resistant for. This is a 2-layer board, so we have a bottom copper layer as well, and then basically just a repeat of all of these. You can go and make PCBs with tons and tons of layers. If you're doing this for hobby projects or basic stuff, 2, 4, maybe 6 is where the sweet spot is. These basically 2 to 8, if you're counting some of the better Chinese shops, is where things are cheap. If you go above 8, the prices get significantly worse significantly quickly. And up at these upper ends, it's very specialized and very expensive to have anything manufactured. Very much can be done, just expect to pay 10x, 100x over what you'd pay down in this range, which are also going to be 10x over what you're going to be paying down in this range. If you're manufacturing in the US for cheap, 2 to 6, some of the Chinese fabs do 8 for pretty reasonable prices as well. So for the purposes of this, we'll stick with a 2-layer board because it's a very simple setup. So the less layers, the less money. Board finish, this is not super important to set. Solder mask and paste, I would just leave as the defaults. Text and graphics, we're going to ignore for the purposes of this. And then we get to design rules. This is basically all of the things that the computer is going to check to let you lay this out in a way that makes sense. The most basic one is you can't actually put 2 parts on top of one another. The computer will yell at you if you try to do that. Why? Because it presumes that you don't want to do that. Similarly, if you have a trace that is set, you're saying this is 3 volts, and another trace that you're saying this is 5 volts, it's not going to let you run those two into each other unless on the schematic you depict it doing that. Basically, it enforces that your schematic governs reality. So anything you want to do has to be drawn on the schematic, and you'll get a bunch of errors if you do something that's not. This is really super helpful. These constraints then set how close can things get to each other, how small can things get. If you set it to 0, it'll let you take it down to 0, but you can say things like, hey, I don't want vias smaller than 0.5 millimeter. Why? Because it's very hard to drill a hole smaller than this. Hey, I don't want my copper right next to holes because if the drill bit wanders a little bit, I don't want to accidentally hit it. For these, in terms of what to set for them, generally, I would basically look at whichever PCB fab you plan to have manufacture this board and copy paste their minimum suggested default settings. For the purposes of this, Oshpark is great. They're manufactured in the US, environmentally friendly, pretty cheap, and they have pretty good specs in terms of like they do pretty nice things for the price. And they have these lovely pages where they detail out all of these settings. And so basically you just go and you copy paste all of these in. If you hop on Reddit or Stack Overflow, there's definitely downloadable files that have all of this already set that you can just set as a default in your Kicad instance. If you're manufacturing overseas, JLC and PCBWay are the usual suspects of places people go. They're very, very cheap. They're not very cheap right now with tariffs. You can see they can make me 2-layer board, about 4 inches by 4 inches, 5 of them for $2. It'll then cost $24 to get it here, with DDP, meaning that a huge chunk of that is tariff. Technically this might get here, but if you have a shipping option that's not DDP, what will happen is you will get a tariff bill sometime after the fact. Delivered duty paid means that JLC will pay the tariff for you, and so they're just rolling in the cost to you. No comments on that, but that's currently something to look out for. If you're buying enough boards, it's absolutely still cheaper. If you're buying two or like just a handful of boards, the like quick turn American shops are currently the cheapest option. Some of the quick turn Canadian ones are also quite efficient. Predefined sizes, this is where you define like how big of a piece of copper do I want to use as a connector for things? How big do I want my vias to be? Since we're running a little behind, I'm going to just set some default settings here that I use that are generally good. 0.2 millimeters is a safe small track size that almost any fab can make. 1 millimeter gets you a lot of power transmitted. And then vias, typically you want the, oh, sorry. It doesn't auto translate, does it? Typically you want them to be about a ratio of, and I did that backwards, like 2 to 1. If you want the outer plated area to be twice as big as the hole, and I know Oshpark can drill that size hole. Everything else on here is not super important for a simple board, so we're going to kind of skip through it. Take a quick look at questions. Yeah, so what do silk screens do? Silk screens, I'll show those in just a minute, but basically they are the pretty white text you see on PCBs that label what is there. So right now we have our outline of an Arduino. We have our parts, and you can see what's called the rat's nest, which is these lovely lines. You can also see that even though this is the outline of something I'm using intentionally, it doesn't want to let me place things on it. So we're going to just ignore that warning for just the moment. But if you click on something that has a rat's nest to it, click wrap single track or hit X on your keyboard, it will then give you a lovely wire. You can go. We can say, hey, we want to connect that to here. And now that ratness line goes away because that's connected. And then go and say, hey, we're going to connect this one to here. I think you can see where this is going. I think you can also see how basically circuit like ICs are never laid out intending for you to route them in your specific use case. So it's guaranteed that at some point you'll have a signal that gets trapped. Hey, there's no way I can make that ground connection without doing some horrible squiggle way up and around, which is a bad idea. How do we get out of this scenario? We route it out, and then we hit a via. The shortcut for via on here is V, so I'm going to just use that. Places a via, and then when you click, now we're routing on the back layer. And blue does not touch red, so we can just route it straight up to where it wants to go. We'll connect those two even. And hey, we can go and do the same thing with this one. We want that to come up here. If you're familiar with circuit boards, please don't yell at me. I'm just laying this out really roughly just so we can get kind of rolling through the workflow. But now this guy's connected to everything that it needs to be. So we can go through and add the other little components that are needed. Bring it up here. If you hit R on your keyboard, it'll rotate. We can go connect it in. This is our decoupling capacitor, which we really want to have closer in. Cool. That helps like stabilize power coming into this guy, and it's now connected where it needs to be. And then here's our two resistors. These guys need to connect one to each of these data lines. And then they need to go to 3.3 volt power. So put him where he drops straight onto that power. We're good. And then basically take this guy and do the same thing. If we want, we'll just put him here. Can route this so that we're connected. And then these through-hole connections are already a via. So if we switch layers and set it so we can only see the active layer, now take this, connect it to where it needs to go. Connect our last ground trace in. And now everything is connected. We don't have any more of those rat's nest lines. At this point, we'd go through, we resolve any errors that the computer finds. We run this thing called a DRC. It says, oh, you've got 5 problems. Most of these are that I'm putting things on top of one another. So courtyards overlap. Board has malformed edges. That's because we don't actually have an outer edge of it. And then we have warnings for silkscreen. So we'll do the edge of the board, and then we'll do silkscreen, and then open it up for questions. For the edge of the board, this edge cuts layer defines physically like what is the outer edge of the board. Typically, it's a rectangle, and you want to just make sure that everything you need is on it. I'm going to make this guy intentionally bigger than we need so that we get all of the labels showing up. But if you were actually making this, you'd probably want to trace this Arduino outline here and make it exactly the same size so that you're not paying for any extra circuit board. Silkscreen is the labels. So each component comes with default labels attached. You can move them around freely as you wish. And these are basically just to help make your life easier when you go and try and assemble this, or if you're debugging or anything, if you can actually figure out which resistor is which. Because it's really great when you have 2 resistors and a capacitor. And when you start doing something more complicated, we have 100 resistors and capacitors. It's really nice to have labels. There's front silkscreen. And similarly, there's also back silkscreen, which I don't think we have anything on for this board. But yeah, this is now a fully defined PCB. If we hit View 3D Viewer, Kicad has a really lovely 3D rendering engine, and you can see there's where our little sensor will go, capacitor, 2 resistors, and then an Arduino compatible footprint. And you can also see depicted here real small all of our little traces for connecting everything. You can pull in 3D models for every single part of the board. It does model all the internal layers. You can see your leads and everything. So this is super helpful because you can also take this and export it into SolidWorks or Fusion 360 or whatever you like, Onshape, and use it so that you can make things like mounting holes. If say, hey, I want a hole here and a hole here, this many millimeters apart, so that it lines up and screws into my chassis. That's all just done as you just are export, and then you're just exporting steps or STLs directly even. Awesome. That's my walkthrough for about the most basic board I could do, and so that I could try and hit time here. I'll stop talking. If any of y'all have questions, happy to see what I can do to help.
I have a question.
Mm-hmm.
So after we complete this board, how do we export it so companies can manufacture it?
Yeah, great question. Glad I didn't have to pay someone to ask that one. So there's 2 ways. Traditionally, you'd save your board and then you go to File, Fabrication, Exports, and you're going to need to export a thing called Gerbers, GBRs, and drill files. Basically every manufacturer in the world will take those 2 files. Some manufacturers will take these 2, which are like more modern things that were supposed to replace them that really didn't. But you go to Gerbers, and similarly, for your manufacturer, you go and you check their list and you say, okay, what coordinate format do they use? 4.6 or 4.5 millimeters? Do we need Protels or not? None of this you really need to understand. You just need to make sure it matches the format that they're expecting. Kicad's default one is pretty close to what most people are expecting now. And then you'd click plot. And this basically, what it's effectively doing is exporting a vector drawing of each layer in a very standardized format that is very similar in a sense to like STLs or G-code, in that it's an intermediate format that you take from your design system and you feed into your production system. So that their PCB manufacturing machines take in these Gerbers and then say, okay, I need to put down copper in these locations and I need to etch it away in these. I need to drill all of these locations and then plate them to make them vias. This is great. This is something you should absolutely play around with and try. If you click plot, it'll generate for me, like in this one, I'd get 1, 2, 3, 4, 5, 6, 7, 8, 9 different files, and then drill will give you 2 more files. You take all of those files, you zip them up, and you upload them to the manufacturer in question. So let's go ahead and do that. That's a good question. Where the heck did I just save that? Cool. Let's put it where I want it to be. And cool. So that just generated all those files. If we open it up, hope it's putting them in there. Yep, you can see all of these GBR files and these 2 DRL files. And what we do is we literally just take all of these, zip them up, and then this is the file that we upload. And we can do that real quick. Additionally, in the last bit, Oshpark is really the manufacturer that I would say kickstarted this, but other places have started doing it. A lot of the more hobbyist-friendly manufacturers have started just taking design files directly. So you can see JLC does not. They take only Gerber files. So we upload this. They will plot it, and they're going to draw you a little image of your board. You set all of your settings, and they'll tell you how much it will cost and how quick they can get it to you. Lovely. Oshpark, these guys will take Gerber files. They also will just take direct native Kicad files, which is super helpful if you're trying to just like test things out quickly. So you just upload your board file directly, and they will plot it out here. Click back. Of course, this is still like cycling. So let's see which one gets it through first, and walk through their order workflow just so you can see it. Great. Detected a 2-layer board. I didn't specify a size very tightly, so 3.3 by 3.13 by 2.29 inches. 3 boards will cost you $35. Generally, if you're manufacturing, especially with Oshpark or DigiKey, the smaller you can get the board, the cheaper. That's not always true. A lot of manufacturers, it's basically just like tiers. So like anything above 2 square inches to 210 square inches is all the same price. These guys charge per square inch, so shaving it down a little bit would certainly help. But then they plot the different layers of it. I'll put in my random email for this. And then they will plot each of these layers. This is effectively the Gerbers that they will be using. And you are responsible for going through and making sure you don't see anything insane on them. Because if it's drawn here, that's exactly how they're going to make it. And they explain what you're kind of looking for. JLC apparently is struggling a little bit right now. But this would process through. Yeah, I don't know where that went. Great. And they make you choose every single specific of it. Oshpark, one of the nice things, every board they make is built to a very high quality set of standards. They're all lead free, and they use what's called ENIG, which is one of the like higher tier process technologies. JLC for the $2 price builds it the cheapest way possible, which is great if you want $2 PCBs. So if you want anything specific, you have to go through and change it. Depending on what lab you're assembling it in, especially, I don't know how MIT is. Harvard, I know, is real picky about this. They need to be lead free. And they do a really good job of explaining like what is each of the differences here. Enig is generally just better than Hazel. HASL, Enig's more expensive. None of these prices are updating. That should have made it go up. That's lovely. Different types of board you can have it manufactured on, which they explained. Basically, higher number is better. Colors, thicknesses, how much copper you want on each layer. They give you all these options, which you kind of need to go through and specify. But that's great because if you want something specific, if you need smaller vias, you can do so, and it will change the price. But they give you the option. Figure Poshmark, the way they get it as cheap as they do, but manufacturing in the US is everyone's boards are built to the same specs. They're quite high quality specs, but that way they can batch them all together and basically make one giant panel and then cut it up to distribute each person their boards. Which was my slide here, which is great. Other questions? Awesome. Well, if we're wrapping up and people don't have questions, other resources I'd suggest, honestly, as with any CAD, build something and then get someone who knows a little bit more than you to tell you what you did wrong. So, like, make a simple board, do a design review with someone who's built a PCB before and ask them what's wrong with this. If you can batch up orders with friends, the de minimis tariffs get a lot worse on $2 PCBs if you're buying like 10 sets of them at once because you're going to pay the same tariff rate as you're still below. So find clubs and order things to test. As boards get more complex, use more of the features of the tool, net classes, setting custom DRC rules. And if you want good examples, I think SparkFun does a really good job of all of their boards have published schematics and typically have pretty good designs. If you're making switching voltage regulators, Texas Instruments Webbench will do the schematic design for you, and it's 99% correct, which is usually better than I will get just doing it on my own. And then generally reading data sheets. Data sheets and application notes tend to have depictions of the circuits in them, and we'll talk you through like what is actually important if you are to implement this chip. Generally, I think Texas Instruments and Analog Devices have some of the clearest data sheets. They're definitely premium parts, so they tend to cost a bit more than especially some of the like more knockoff brand or some of the more up and coming Chinese brands will run. But their data sheets are very clean and clear. Some of those up and coming Chinese brands have really good ones as well. ESP is definitely getting much better at their data sheets. And if you want a great first semi-complicated project, I think taking Raspberry Pi's like hardware implementation guide, if you just Google RP2040 minimum viable board, they basically have this like 40-page PDF that walks you through how to prove that this chip works, which is what are the minimum things you need to put on a circuit board with it to have it show up and be programmable from your computer and be able to blink an LED, be able to toggle GPIOs and talk to things. This is really nice because they did it kind of intentionally as minimum viable. If you're working with any other microcontroller board, they're going to have all sorts of things baked in from the start. But this one gives you a really good like starting place where once you know that that board works, you then can make your custom version with other stuff. Why did I go into hardware engineering? I thought I was going to be a pure mechie. I did rockets and rocket motors in high school and really thought that was kind of where I was going. Big space guy, still a big space guy. And hated electrical engineering when I took it in college. Found it super complicated, super esoteric, very heavy on like the theory and not very practical. Also just didn't enjoy the first class, but loved the lab portion of it. Why did I get into this? I was the first employee at a startup that was doing sensors, and once I got our buoy at the time working properly, we really needed to customize some sensors, and so I figured I'd learn how to do that, and I've basically been doing that ever since. Nowadays we're at like 40 people, and I still do mostly circuit board design, which I've grown to really, really enjoy. Yeah. Anything else? Yeah, of course. It's really great. The KiCad's free. It's a really awesome tool to have learn and work with. And it's definitely something if you're going to a startup or to any sort of like electrical engineering or like IC or circuit board design firm, it's definitely great to have some like hands-on experience. Um, as someone who hires co-ops and undergrads, um, everyone kind of takes the same core EE classes, but like knowing that you know how to implement is really like a super useful skill to have for sure. Yep. Yes, I will be wandering around this weekend. So if you've got circuit questions, you can find me. Yeah. It's certainly a great way to level up your design over a bunch of jumper wires and a breadboard. As someone who's done a fair bit of hackathon stuff, it's always really great when you go to judging and somehow it all falls out of the breadboard right then. Yeah, awesome. See y'all Saturday. Hope everyone has a good evening.